We have a variational expression over here. The question is, can you find its corresponding Euler-Lagrange equation? So pause the video to do that, making use of this slightly intimidating looking formula over here. So we start from a variational expression. Let me copy that over here. So j of phi is the integral of f and then the square of the gradient of phi ds. And in order to minimize this variational expression, we're going to look not only at phi, but also at neighboring functions, neighboring points in the infinite dimensional space. We're going to look also at phi plus delta phi, and then evaluate the functional at that neighboring point. And that we're going to use to calculate the first variation, so the difference between these two things. And that should be 0 if we're working in a minimum. So let's see what that amounts to. So that's again the two-dimensional integral of f. And then we have the square of the gradient of phi plus delta phi. Gradient is pretty linear, so the gradient of phi plus delta phi is just the gradient of phi plus the gradient of delta phi. So gradient phi plus gradient of delta phi, and then that whole thing should be squared. Let's expand this to have f gradient phi squared ds, and then we have plus 2 integral f gradient phi gradient delta phi ds, and then finally we have a term which is f gradient delta phi squared ds. Good. So now let's have a look at the first variation, which is just j of phi plus delta phi minus j of phi. So now we're in a position to calculate that because we have explicit expressions for both of them. Let's do that subtraction. So first of all, this thing cancels, so that's good news. And then we have that term over there. That's 2 times the integral of f gradient phi gradient delta phi ds. And then we have a term which is on the order of delta phi squared. So we're going to neglect that compared to a term which is just linear in delta phi. So this is approximately equal to the first variation. Good. And this thing should be equal to 0. That's our goal. We need to find functions phi which minimize this thing. So the question now is, once we are at this stage, can we now use this equation that we had up here, this particular equation? Can that help us to find the Euler-Lagrange equation of our variational form? So this might be a good point to pause the video and take the next steps yourself. So let's copy the formula that we're supposed to use. So it's P, and then we have gradient Q, gradient R. Let's try that one again. Gradient R ds, and that's equal to minus, and then the integral. We have Q, we have a divergence, and then we have P gradient R ds, and then we have some terms over the boundary delta s. Now, just like before, we're going to neglect that term. Well, neglect, at least say that it doesn't play a role in our particular case, either because the functions or their derivatives vanish at the boundaries. So let's not worry about that term, and let's assume that in our case it's 0 anyhow. Okay, so how can we make use of this function? Well, looking at the structure here, it's obvious that this guy maps onto that guy. So that also means that P in our case should be F. But then we still have some symmetry in between these terms. So it's not immediately obvious whether Q or R should either be phi or delta phi. But then let's have a look at the right-hand side. And let's not forget what our aim is. Our aim is to derive the Euler-Lagrange equation, which is typically done by having an integral of this particular form here, where we find a product of delta phi times something should be equal to 0 for all possible values of delta phi, so that we can conclude that then that second term should therefore be equal to 0. So bearing this in mind, this means that our Q in this particular case should be our delta phi, and R is then just phi. Okay. So now that we've done that, the conclusion is that our first variation is 0 when we have minus the integral of delta phi, and then we have, so P is again F, and then we have the gradient of phi ds. So this thing is 0. The important thing to realize is that this thing is just not by accident 0 for a well-chosen value of the function delta phi. No, this thing should be 0 for all possible values of delta phi that you can think of, and even those that you can't think of, in order to really have an extremum of this functional. So this can only be true for all possible values of this guy if this factor here is actually equal to 0. And that gives us our Euler-Lagrange equation. So we should have that the divergence of f gradient of phi is equal to 0. So there we have our Euler-Lagrange equation for our variational expression.